Hi friends, this is Professor Ravi Mishra and I'm here to just give you a little piece of demonstration about the subject Applied Mathematics 1, which is there in first semester of engineering, which you are planning to get into. Generally people have this thought process or this thing in mind that the Applied Mathematics 1 or the mathematics subjects that you are going to have in engineering is almost same as 11th and 12th standard. I will disagree with that because first of all it is not Maths 1, it is Applied Mathematics 1. So there is a difference. Whatever we have in engineering is something which we call as applied mathematics. Now applied mathematics means here you will study those techniques, those concepts which you will really apply in engineering field. Like complex numbers topic if I talk about. This concept you will be using in BEE as well. The BEE, this is again a subject in your first year engineering, that is semester 1 only. So let me just take a small question from the topic complex number. However, the topic is quite vast and it has a lot of things into it. If you ask any of your senior, they will say beware of this complex numbers topic in Applied Mathematics 1. Usually people study other topics and they try to leave this, which is obviously not a right thing to do. So let me just explain you complex numbers. This is a topic which some or the other way, somehow you'll be aware of. Like I can say you have done this in 11th standard or your previous academic maybe. And complex numbers topic, I mean the terminology you are not new with. First, let me tell you few basics about complex numbers, something that you are already aware of. Any complex number we represent by z, and complex number is what? X plus iy. If you represent any number in this particular form, we call it a complex number. Now what is this I? I is basically square root of minus 1. So if suppose I get square root of minus 2, I can write it as square root of 2 into square root of minus 1, which is basically square root of 2i. So if you get square root of a negative number, we call it complex number. Now we are studying complex number in first year of engineering. The first number system for engineering is complex number. Why? Because complex numbers is a part of number system which is above every number system. You must have as of now we use real number system. Complex number is above that. Like if I say 2 plus 3i, now you will say yes, obviously it is a complex number because the complex number is of the form x plus iy, where x we call as real part, y we call as imaginary part. So here, is this a complex number if I ask you? Yes, obviously it is, and real part is 2, imaginary part is 3. If I ask you this, minus 7i, is this a complex number? Yes, obviously you can say this is a complex number. If I write 0 over there. So it is again a plus bi form, where real part is 0 and imaginary part is minus 7. So that plus factor is adjusted over there. What if I ask you this? 3. Now this is a real number, but yet again I can say this is also a complex number if I write it like this, 3 plus 0i. So everything it comes under complex numbers. Like initially when you were a child, so they used to at home they used to teach you beta 1 2 3 bolo, 1 2 3 bolo. Nobody ever told you beta minus 1 minus 2 minus 3 bolo. Because if they do that, you will never go into school. They won't teach you from 0, 1, 2, 3, they won't teach you negative numbers. Slowly, gradually you understand. So 1, 2, 3, 4, 5, natural numbers. If you include 0, we call it whole numbers. If you include negative numbers, integers. So slowly in our academic, we understood all these number system. And the topmost of it is complex numbers. Well, so x plus iy is this form. We call this as Cartesian form. Z can also be written as r cos theta plus I sin theta. Now in our batches obviously we'll focus more on this. How we get from this to this, Cartesian to polar. So polar form is represented like this. Now again this is also a complex form only because it includes I. So r into cos theta plus I sin theta. Now this we call as polar form. Why do we need polar form? Because complex numbers, if you want to solve in practical, it is more and more easy if you apply polar form. So that's why we need to understand this form as well. Now in this you can see r and theta. What is r? R is nothing but modulus, which is basically square root of x square plus y square. That's real part square plus imaginary part square. Theta is something we call as an argument, or it is also called amplitude, which is nothing but tan inverse of imaginary part by real part, tan inverse of y upon x. So if you have a particular number in Cartesian form, you can convert it to polar, because now you know what is r and what is theta. And similarly vice versa, you can go from this to this as well. Now the very first topic in complex number, you are going to study a theorem called de Moivre's theorem. Now it is not simply a theorem, there is a complete topic based on it. First part of complex number is completely this, de Moivre's theorem. Now I'll explain you de Moivre's theorem, but before that I'll ask you a few questions. What if I ask you to find cos theta plus I sin theta square? Well, you can do it. It's quite easy. I'll apply formula A plus B the whole square. A square plus 2AB plus B square. Well, you can do it. Fine. Let me make it a bit complicated, as we are getting into engineering. We have to prepare ourselves for that. Cube. Again you can do it because you know A plus B the whole cube ka formula. Let me make it raised to 4. Still you will be able to try. Why? Because raised to 4 can be written as this square into square. So we'll make squares and then multiply. What if I give you this? Raised to 40. What if I give you this? 400. So if the number is beyond our limit, I mean we can obviously solve this as well, but it will be like too tedious. Maybe pura semester chala jayega. So we won't be doing that. De Moivre was the one who gave a workaround for it. He said, no matter what power is raised to n, the answer is always this, cos n theta plus I sin n theta. So if somebody asks you raised to 40, the way I asked, the answer is simply cos 40 theta plus I sin 40 theta. Whatever power it is, you simply have to multiply that. That's it. That's what we have as, that's what we call as de Moivre's theorem. Now see, if you actually go to find raised to 40, means square, multiplying again and again, opening the bracket, it will be very tedious. The ultimate result will be this only. How beautiful this formula is. And that's the magic of de Moivre. This concept allows us to solve many engineering applications, many real engineering applications. So I'll just take a small problem which is there in front of you, and let's see how de Moivre's is useful in solving such problems. Obviously when you'll come to our batches, you will see that we'll be solving variety of problems and number of concepts. Along with this formula, again we'll manipulate these formulae and we'll have a list of formulae. But as of now, let's concentrate on this question. The question is, if alpha and beta are the roots of this equation, what type of equation it is? Quadratic equation. Yes, quadratic equation. Alpha and beta are roots. Obviously quadratic ke liye we have always two roots. So alpha and beta are those two roots. Then you have to prove that alpha raised to n plus beta raised to n is equal to this. And hence you have to find alpha raised to 15 plus beta raised to 15. Now this is what I was talking about earlier, engineering. Now you will have problems which won't be so direct like the way it was there in 12th standard or 11th standard. It is going to be somewhat different. I will not say difficult, different. Alpha raised to n plus beta raised to n is what you are looking for. You know alpha and beta are simply roots. Raised to n means any general number. Now instead of n I can have any other number. So they want you to generalize it first. So what I'll be doing? We know one thing, that alpha and beta are the roots of this equation. So let me just consider that equation. So equation is x square minus 2x plus 4 equal to 0, and alpha and beta are the roots. We'll do one thing. This is a quadratic equation and we know how to get roots of quadratic equation. So let me find it. Since therefore roots are x equal to, now I hope all of you remember, root is given by this, minus b plus minus square root of b square minus 4ac divided by 2. This is what we have as root of any quadratic equation of this form, ax square plus bx plus c equal to 0. Now if you look at this quadratic equation, a is 1, b is minus 2, c is 4. So the roots will be minus b is minus 2, plus minus square root of b square, minus 2 square is obviously 4, minus 4ac. Now 4 times 1 into 4, it's going to be 16. Divided by 2a. So that means x square coefficient, which is 1, 2. So I am getting root of x as minus minus will be plus. 4 minus 16 is minus 12. So I am getting x as 2 plus minus. Root of negative is obviously I. What else? Square root of 12, which can obviously be written as 2 root 3, something that we are already aware of. 4 3s are 12, 4 square root is 2, so we can take it outside. So I can write it like this. And you can see that 2 is getting cancelled if you take 2 common. Now we don't need to show that step. What I am getting is this. Roots of this quadratic equation are 1 plus minus I root 3. As I said, obviously, in quadratic equation we always get 2 roots, and here we have 2 roots. They have said that the 2 roots are alpha and beta. That means they have basically given name for them. Fine. I can write one of the root as alpha. I'll first give a reason as alpha and beta are 2 roots. So what will be alpha? I can take 1 plus I root 3 as alpha, and beta as 1 minus I root 3. So I have taken positive root as alpha and the negative one as beta. Obviously you can also take this as alpha and this as beta. There is no condition towards it because they haven't specified as such. So I'm having alpha and beta. Now look at the question. You want to prove that alpha raised to n plus beta raised to n is equal to this. Now obviously this looks quite horrible. Let's not get into it. I'll concentrate on this. Do I have alpha? Yes, I have. Do I have beta? Yes, I have that as well. Raised to n. N is any general number, so I don't have to bother about it. If alpha is this, can I find alpha raised to n? Suppose I take nth power of this. Now see how complex number is going to play with you. 1 plus I root 3 raised to n. Do you think without knowing value of n, you can expand it? No way. It will be an infinite term series, basically n plus 1 term series. So obviously I won't solve it by that particular way. 1 plus I root 3 raised to n. So if there is a power of a complex number, is there any theorem, is there any method which can help me? And there it comes, de Moivre's theorem, which says if you are taking power of cos theta plus I sin theta, any power n, then they become multiple of angle. Simply they become multiple of angle, that's it. But there is a condition towards it. Real part has to be cos and imaginary part has to be sine. So do I have, here in this case, cos and sine ka term? No, that's again a problem. Can I make it in terms of cos and sine? I will try. See, I can do one thing. I can multiply and divide by 2. And if I do so, the term will look like this. I'm just talking about alpha as of now. 2 I have multiplied and 2 I have divided inside and separated as well. You will say why we are doing this, or how come we know we have to do this. It's just because of this. Half. We know one thing. Half is nothing but cos 60. Cos 60 is half. Secondly, this is root 3 by 2, which is nothing but sine 60, which is pi by 3. Pi by 3. Pi is 180, so divide by 3 obviously is 60 degrees. I can write real part as cos. Now see, again you must be having one thing in mind. Even sine 30 is half. So why am I not writing sine 30 over here? That's because of this condition. De Moivre's is asking for a cos term first. Real part as cos. So that's why this is a way of writing alpha. Fine, I have alpha. Similarly, I can find beta as well. But I'll do one thing. I'll first concentrate on alpha only. I also want alpha raised to n. This is what I'm looking for. So I'll take nth power. So this will become 2 raised to n as they are multiplied. So raised to n will come with this as well as this. I sine pi by 3 raised to n. Now let's go for De Moivre's theorem. So De Moivre's, he made our life very simple. He said whatever power you have, just simply make them multiple. So alpha raised to n will be 2 raised to n cos n pi by 3 plus I sine n pi by 3. This De Moivre concept will also give you quite detailed knowledge of roots of a complex number, that roots of unity 1 omega square, which you are doing in 12th standard, 11th standard. Fine, so I have alpha raised to n, but I am looking for beta raised to n as well. Beta raised to n. Now beta also I'll do the same thing. I'll multiply and divide by 2. Then I'll write in terms of cos and sine. But do I need to show those steps? No, not at all. Complex numbers has one thing very interesting. If anything happens to this, similar thing will be reflected to its conjugate as well. Now this is simply a conjugate. Sign of I has been changed. So you never solve for the conjugate term. You can directly write similarly beta raised to n will be 2 raised to n. Now here you have a change of sign only. So the same thing will reflect over here as well. It will be cos n pi by 3 minus I sine n pi by 3. That's it. Finally, what you want to add them. So I'll simply add them. Adding, we get alpha raised to n plus beta raised to n. When you add, you can see that 2 raised to n is common. So I take it outside. And when you add these two brackets, this will be added and this will get cancelled as the sign is different. Plus and minus, they will cancel. So I am left with 2 cos n pi by 3. Now this is 2 raised to nothing bole to 1. So what I'll be doing, I'll simply add the power. 2 raised to n into 2 raised to 1 is nothing but 2 raised to n plus 1. And it is cos n pi by 3. This is what we had to prove, and it's done. Secondly, they are asking you to find alpha raised to 15 plus beta raised to 15. Do we need to worry about it? Not at all. If you know alpha raised to n plus beta raised to n, your first proof is done, first question is done. For the second one, what I'll be doing? Simply put n as whatever they are asking, n as 15 in equation 1. So what do we get? Alpha raised to 15 plus beta raised to 15 will be 2 raised to 15 plus 1, 16 cos, now put 15 over here, 15 into pi by 3, 3 5s of 15 is cos 5 pi. What is cos 5 pi? Now for this you don't have to look into the table or anything. This is what engineering is all about. There is a direct formula for it. If you get ever cos n pi, its answer is minus 1 raised to n. Cos any number into pi. So here it is going to be cos 5 pi. So it will be, if it is 5, minus 1 raised to 5. 5 being an odd number, minus 1 raised to odd will always give you minus 1. So it is basically 2 raised to 16 into minus 1. If it is an even number, it will be plus 1. Directly you have to write this answer. You don't have to even solve it in Calci. So my final answer is minus 2 raised to 16. This is what we have a gist of this de Moivre's theorem in complex numbers I just gave you. Further, after this complex numbers, you have again hyperbolic functions, log of a complex number, and there are many more to come. If I talk about other topics, partial derivative. In your earlier academies, you have done normal derivative. Here you will be doing partial derivative. Then matrices will come. Obviously, it's not as same as what you have done in 11-12 standard. It's different. It's further part of it. Then you have successive differentiation. You have done differentiation, means derivative. Here you will be studying successive derivative, means differentiating 1000 times, differentiating umpteen number of times, n times. That is what you are going to study here. Expansions, limits, series and all. Many interesting topics are there in Applied Mathematics 1 as well as Applied Mathematics 2. In fact, I can say full semester 1, Mechanics, BEE and Applied Mathematics 1, all are very, very interesting subjects. So I just wanted to explain you that yes, it is a bit different than what you have been studying in 11-12 standard. It is going to be different. That's why the name is different. It's not Mathematics 1, it's Applied Mathematics 1. The knowledge of which will be very much used in engineering applications and in your engineering career. So further part of this, next part of this and remaining portion we will be doing in our batches. You can visit any of our centers. You can your nearest center, and you can check with the staff about the batches. So let's see you. I hope we'll see you again in our batches. Thank you guys. Thank you.